Hi, this is Steve, V6WZ. Up at the remote today. It's actually a pretty cold day. It's warmed up a bit. Right now it's minus 33 degrees Celsius. The low to last night was minus 38. Well, it's getting close to, for those of my American friends, that's close to minus the same, minus 38 or almost minus 40 Fahrenheit. It's really cold out here. Hey, look, the reason I'm out here, I'm going to do some experiments. Come and join me because I've had some interesting results with my beverage antennas, and I've always wondered about frozen ground and the effect of conductivity, and I've noticed some changes. So, hey, let's go inside, and I'm going to show you what my thoughts are. I'll show you some of the measurements. Then I'm going to go out in the field. We're going to do some experiments with adding some radials to the both the feed point and the termination on my beverages to see if that'll change things. This is truly an experiment. I don't know if it's going to work, but hey, why don't you join me here and we'll see if it works. All right, hang on. I gotta get into the radio room here. Fortunately, it's heated, although I'm gonna have to turn the heat up a bit. All right. We are inside the radio room. This isn't normally how I'd like to do this kind of video. I'd normally just do a screen recording, but in this case I just wanted to do it all in real time. So I brought up the AIM analyzer here. That's what this window is, and I'm gonna just look at the one beverage. This is my East Beverage. It's a single wire rather than a one of my broadside phased pair, and this is the one I want to do the experiment on. But I assure you, I have done this same analysis on every one of my wires, and they're all showing this same effect. Well, let me show you what that is. All right, so as I think, if you've watched any of my other videos, you'll know what I do is I save files of the analyzer sweep of every one of my beverages. And so, for example, I'm going to load the graph here for what I call my East wire, all right? And this was done back in September 2019, when, of course, the ground was all nice and normal, all right? And the AIM plot goes from 0 megahertz, right, all the way up to 8 megahertz. In the red line is the SWR sweep, and up here, I think it's the orange line is the series resistance. But you'll notice if I put my cursor like right around here, this is around 1856 if you look up here, and I can see that my series resistance is about 78 ohms. So, pretty close to a match. By the way, this particular sweep is calibrated to the box out in the field. That is to say, I actually calibrated the analyzer from the shack to the box, doing an open, short, and load out there. So it's kind of sort of accurate. All right, now normally, during the season, throughout most of the time, if I do another sweep of the actual wire and do an overlay, it'll be almost an exact match. Well, let me do that now. I'm going to do what's called a rescan, all right? And I'm hooked up to the East Beverage wire, this same wire. There we go. We're doing that sweep now. All right, you'll notice here, the SWR is way up to 3 to 1, all right? But it sort of matches down here. And this is the same thing that I've seen on every one of my wires, this same effect. So again, if I sort of put my cursor around the same point here, around 1850, you'll notice, okay, look, I'm almost well over 2 to 1, and my resistance is down. It's around 54 ohms. And look, I'm not quite sure what this means, but I've got some ideas. So hang on, I'm just going to do another little, I'm going to give you a brief story on what I think might be happening and what I'm going to try here. All right, so here I've got a diagram of the anatomy of my beverages, or any typical beverage. I've got the feed point here with my matching transformer, matching the impedance to my coax. And of course the beverage wire is shown here, and at the termination we have our termination resistor. Of course at both ends we have our ground rod. In my case I use 3 foot, sometimes 4 foot pieces of copper pipe, a water pipe driven into the ground. In most cases I'll have 2 at each end, separated by about 3 feet. And of course the same is at the termination end. All right, here's the thing. Most of the time, of course, these copper pipes are sitting in soil, which is a mixture of lots of minerals and associated salts with the saturated soil and water during the year, which of course is quite conductive, and that represents
represents our, ground conductivity. Okay, here in Canada and in perhaps some other places, but definitely not in the southern climates, this wouldn't ever be an issue. But here's what I'm wondering. Okay, we've got this thing called the frost line, which can be driven down, as far as 6 feet. During the the middle of the winter time. Well, okay, now what's happened? Well, what we've got now, these copper pipes are, they're sitting in an ice cube right now. I mean, it's a block of ice here. So what I'm wondering is, I have trouble imagining any kind of ionic conductivity or ionic transfer from the standpoint of conductivity when it's sitting in a block of ice. So my question is it possible that we basically lost our ground conductivity because of the frost? I mean, the fact of the matter is, it's a little confusing because I just showed you my sweep, and for some reason my actual impedance on the 160 meter band at least is down around 55 ohms, which is a bit confounding, but perhaps that has something to do with the termination. So here's what I'm going to do. I'm gonna make up 4 radials. I'm gonna cut 4 pieces of just house wire. All right, I'm gonna solder them together here in the shack when it's warm, and I'm gonna put an alligator clip on them. And I'm going to go out and attach those and have them, just laying on the snow, okay? This would not be a permanent installation, but it's an experiment. The idea is that maybe, through just capacitive coupling with the ground, I'll enhance or otherwise regain my RF ground here. I mean, these are not resonant, but, I'm hoping that maybe that will change things. As I said, look, this is an experiment in real time. I don't know if this is going to work, but you join me for the ride here, and we'll see if it works. So I'm going to make these wires up now here in the shack out here at the remote, and then I'm going to head out in the field. I'll take you with me here, and I need to be pretty quick out there. It's as I said, currently minus 33 Celsius, and the wind chill is forecast to be up to minus 45, which it can be a bit dangerous, with wind chill like that. Your exposed skin can freeze in about 10 minutes. So, I'm going to have to be pretty quick. I'm going to go do that both at the termination, and at the feed point. Come back and let's do a couple more sweeps and see if there's any change. I mean, maybe there won't be. Anyway, it's going to be interesting to see.
All right, I was able to get this done. I was able to do it without even having to take my gloves off. This is the feed point for the east wire, and fortunately the ground rod was fairly accessible. You can see that's one of them, and another one over there, and that's the feed box. The copper pipe is fairly corroded, but I'm hoping I've got decent connection with that alligator clip. I mean, I've kind of scored it a bit. Maybe that's not the best, but let's go see what we see. So each one of these wires, as I said, is about 40 feet long. I just laid them on top of the snow, tied them off to a log or a tree or something, and went in as best as I could determine, fairly opposing directions to maybe cancel any aberrant radiation from them. Anyway, let's go back to the shack now and see if this made any changes.
All right, here we are in the shack. Still out of breath from climbing through the snow. What I did was I saved that graph. See, east wire here, January 14th scan. That's the scan of the before we added these radials to the feed point. So now I'm going to do a rescan. And, well, there you go. That effort proved to be pretty much worthless. Well, no experimentation is worthless. I mean, an experiment's an experiment, and that's the result. And that is to say, very nominal change, perhaps a little bit. You'll notice down here there's a little bit of change. But really on the front end, around the 160 meter, the low end of the low frequency part of the sweep, there's really not much change. So look, I got thinking here, how about, I don't know, this might be not 100% consistent. Well, it's not consistent with my original plan, but you know what? Rather than going through the effort of cutting up another 4 set of radials, given that I saw no change here, how about I go and yank these radials off of the feed point, and then lug them down to the termination and install them there and see if there's a change. Given that there was no effect here on this feed point, or limited effect, I think I'm safe to say that we don't, they're not doing anything here. So let's just move them to the termination and see if that makes any difference. All right, let's head out there again.
Okay, just an update. Before I pulled the wires off of the feed point, I did bring out some steel wool just to be sure, and I polished the rod and made sure I had a better connection, and I did a re-sweep, and no, it didn't make a difference. So it's not a poor connection. I just wanted to make sure I eliminated that possibility. All right, I'm going to pull these wires off and head down to the termination. All right. Okay, still out of breath from running these wires and schlepping down here, but okay, so we had a problem. Turns out, I don't know, maybe the cold, or maybe I did a bad strip on the wire, but one of the 4 wires broke off of my solder connection. And of course, I'm out here at the termination, and I didn't bring any side cutters or strippers with me. So I'm just going to stay with 3 wires. Anyway, this is the termination point, and I also cleaned the copper with some steel wool, so I made a better connection, or I've got confidence in the connection. So I've got 3 wires, so they're sort of quasi-symmetrical, but of course, because there's 3, they're not geometrically opposing, to the extent, maybe there could be some issues with, them not canceling radiation. But, I thought rather than walk all the way back and get some strippers to hook up the 4th wire, while I'm here, I'm just going to connect this, and if there's going to be a change, if this has an effect, heck, I ought to see it with 3. Whether there's 4 or 3, I don't think it should make a difference. All right, I'm going to head back up the hill, and let's do some tests and see what we get.
All right, we're back in the shack. I've loaded the graph of the wire that we did first thing in the morning before we've added any radials to anything. So this is the original. Let's do a rescan. And there you go. So adding those 3 radials at the termination has made no difference. We have not really affected the change in the sweep at all. We're still ending up with this diminished impedance or resistance at the low end of the frequency sweep. So I'm left with wondering what's going on. I'm going to be thinking about this for a little while. One thought that I did have, well, I got a couple thoughts. One could be that rather than there being a change in the actual resistance, as it were, because of the frozen, the conductivity at the ground rods, I wonder if perhaps the entire change of resistivity and the ground quality, as it were, along the entire length has changed such that it's changed the overall characteristic impedance of the beverage. Well, I don't know. I mean, that's a possibility. Here's another thing I'm thinking of, and I got to do some calculating and some online research, but, what is the temperature coefficient of this, galvanized steel wire? I'm going to do some research and look at different metal types and the effective temperature. If I come up with anything of interest, I'll maybe include that at the end of the video. Hey, one other thing I want to be clear. I mentioned at the outset, guys, that this is, I'm testing the East Beverage wire, but I said that this is the same on all the wires. In fact, let me do that. I'm going to do that right now, just so you can see what I'm talking about here. I'm going to load. Let's look at the southeast wire. Okay, I'm going to load that graph. So this is what the southeast wire should look like. I'm going to go over here to my beverage controller on my main PC that I use. So I'm going to select the southeast beverage. So now we got that wire here. And now let's do a rescan on this wire. And look at that, same thing, exactly the same thing is happening here. Down at the lower end, we've got, more like 50 ohms of series resistance, down in the low frequency end. So, and I've done this on all 12 of them. So I just want to be clear with you guys, this is not specific, like there's something wrong with this particular wire. It's happening to all of them. Alrighty guys, I'll let you go. If I think anything else to add at the end of the video here, if there's enough time, I might do that. But look, I hope you enjoyed the adventure with me. You could say it's a failed experiment, but I don't think any experiment is failed. I mean, I've eliminated this as the possibility, and I wanted to do it this winter. I didn't want to go out there this summer and add sort of these radials to the termination and the feed box and all my beverages, thinking that it might help, when I think I've given pretty good evidence that that's not the issue here. Hi guys. Okay, hang on. I did a little bit of thinking here, and I'm going to share these thoughts with you.
regarding another possibility here, and that is the change in conductivity of the wire itself and what might be happening to the termination resistor. I have another video that I encourage you to watch if you haven't seen it before, but I actually, in the field, made measurements of the beverage wire, and in fact, the exact wire that I was doing this experiment on, and measured the exact impedance of the wire yeah, in the field, as I say. I also explained basic, the anatomy of a beverage in terms of it, being described as a transmission line with the beverage wire itself at some height above the ground being one half of the transmission line and the other half being made up of the ground, kind of just like a piece of coax. And the key is to terminate that in its characteristic impedance. And we can calculate the characteristic impedance. It's quite simple. It's a function of the height above ground and the diameter of the wire. And I did a couple of those calculations from 6 feet to 10 feet high and calculates that the impedance should be somewhere between, say 500 and, 529 ohms. Well, in fact, I did a measurement of the wire, and it turns out to be about 519 ohms, all right, on that wire, which is a little bit lower than I thought because, of course, you need to add the ground resistance to this. So it should have been maybe closer to 600 ohms. Nevertheless, I got a fairly decent match with my 470 ohm termination resistor. But you could suggest perhaps maybe it's a little bit high. But nevertheless, it looked like a decent match. Okay, but hang on. So that resistance that we're measuring is partly, at least, a function of the actual real resistance of the wire itself. All right, as well as the termination resistor. So, okay, what happens when a wire gets cold? Well, typically, okay, so we're not talking cryogenics here, but all metals, most metals, when they get cold, lower, their resistivity gets lower. And there's a way to calculate that. It's based on the temperature coefficient. The one thing I had trouble finding, believe it or not, with this electric fence wire is I could not find anywhere online with reliable quotes as to what the actual resistivity per foot or per kilometer was. So I've done some estimations anyway, and I kind of estimated based on some numbers I was able to find that perhaps this 920 foot long piece of wire has an original resistivity about 50 ohms. Well, I've done two measurements, one at 50, or calculations, one at 50 ohms, and well, what if it started at 100 ohms? Well, what we can do is using what's called the temperature coefficient, which is a function of the metal, and I'll talk about that in a minute. If we start at 20 degrees Celsius and then go down to minus 30, that's our 50 degrees Celsius temperature change that I've been experiencing. What that says is that our final resistivity of that wire would, drop to 40 ohms. In other words, 10 ohms lower. Did the same thing starting with an original 100 ohm resistance of the wire. Well, it would drop to 20 ohms. Again, this is using the temperature coefficient of copper. You'll see they're quoted down here in this chart. All the different metals are kind of comparable, kind of similar, except one thing that stands out is iron. Steel. Well, of course, the wire I'm using is galvanized steel, but of course it's coated in a zinc and other alloys. It could even be cadmium for all I know. But anyway, just as a sensitivity measurements, what if I used the temperature coefficient of iron? Well, that would still, that would only change this to, instead of 20 ohms lower, 25 ohms lower. All right, so lowering this temperature could drop our resistivity anywhere from 10 to 25 ohms. So therefore, if that happened, I mean, that's not a lot, but nevertheless, let's say that now our surge impedance has dropped 20 to 25 ohms. Well, what that would mean is we require a lower termination resistor. We need even a lower resistance value. Well, here's the very interesting thing I discovered. These are the resistors I'm using. They're a ceramic device, and the reason we've selected a ceramic device is because you notice here they've got short time overload ratings. Because of the ceramic, they're a little bit less sensitive to high overstress on a voltage, and perhaps this could help survivability with a lightning hit. And also, of course, they're non-inductive, but they are ceramic. These are a ceramic type. And the interesting thing, if you'll notice down here, the temperature coefficient is negative 1300, plus or minus 300 parts per million. So when you see a negative temperature coefficient, what that means is it's not acting like a piece of metal. These resistors will actually increase in resistance when the temperature drops. So, I mean, I could do the math myself, and I did, but there's also an online chart here by the Vichy company. You can find this online. So you can use this online calculator. So my resistors are 400 and, well, I'll show you in a minute. I actually measured this, but, you know, I measured one of them at 479 ohms instead of 470. But we can then input the you know, the temperature coefficient range anywhere from 1,000 to 1,600. Of course, that's because, you know, this is their plus or minus range. You know, it's 1,300 plus or minus 300. And then I can put my starting temperature of 20 degrees. My ending temperature is minus 30. That's my temperature range that I'm seeing in the field. Therefore, this resistor now can range anywhere from 500 to 517 ohms. So if you're following me here, this now is making the problem even worse, because the lowered temperature on the wire is suggesting I need a lower termination resistor, but meanwhile this resistor is actually going up 30 to almost 40 ohms. Let me just show a quick video. I actually made a measurement of these very resistors by pucking it outside and measuring the temperature resistance and then measuring it inside.
Okay, making a measurement here of these Ohmite OY471KE resistors. These are the ceramic resistors, about 474 ohms. It's kind of cool here in the basement, rated at 470 ohms. So let's put this puppy outside and see what it does. It's about minus 30 degrees Celsius right now outside. My outdoor temperature probe right now, or my local temperature gauge, is showing minus 29 Celsius. So anyway, I've got that resistor outside. Let's go and take some measurements. It's been sitting outside for about an hour. All right, here's the resistor measurement right now, 515 ohms at, what did we say, minus 29 Celsius. So real cool, a negative temperature coefficient. Not what you'd expect from a metal, but again, a ceramic device shows this. I think this will compare favorably to, or agree with the temperature coefficient numbers quoted in the data sheet.
All right. Well, anyway, there's some pretty cool stuff. I would, just to summarize those calculations, again, suggest that the cooling of the wire would necessitate a termination resistor, 10 to 25 ohms lower in value, and meanwhile the cooling of this ceramic resistor is actually increasing my resistance, up to 40 ohms. So we're really complicating things here, where could have a deviation of the preferred termination of 50 to 60 ohms from what I'm normally seeing at the ambient summertime temperatures. Okay, here's the thing. The truth of it is, none of this is really material. This is in fact an example of a solution looking for a problem. This is more out of interest, because in actual fact, a slight mismatch, or even a mismatch that I'm seeing, which I consider to be slight, though it affects the SWR and shows that the SWR isn't as flat as we would like, having the beverage not terminated in its exact characteristic impedance, from what I've read, has the greatest impact on the front to back, and even then only a nominal effect on front to back, while if you do the modeling, only has a minimal effect on the RDF, in other words, the total received directivity pattern in the 3D space, which is what really matters. Having optimal rejection off the back isn't always the most important parameter. So in actual fact, this doesn't really need to be solved. It's more of a project out of interest and a little bit of investigation. But I do promise you guys, what I'm going to do is this summer do another sweep and make sure that everything is recovered back to what it was originally. And what I might also do is actually put a resistor on there that would represent this equivalent mismatch that we're seeing today, and see if I get a similar result. Of course, I could go out there today and put a lower resistor value on the termination. Problem is, today it was minus 41 degrees Celsius with a wind chill taking it to minus 47. So I don't think I'm going to do that.
Hi guys, here we are back at the remote. This is about a week after the last video I made, and it's warmed up out here. It's now minus 1 Celsius instead of minus 33. So, you know, we've, you know, it's warmed up like almost over 30 degrees Celsius. So what I've done here, look, I've loaded that same graph. This is the graph from the last time when it was cold and we had this very high SWR and diminished or decreased series resistance. I'm going to do a rescan. Well, look at that. All of a sudden my SWR is quite a bit lower. In fact, this is looking very much like it did in the summertime. In fact, you know, you can see the series resistance is down around 70 ohms. So all of a sudden things have changed here. It seems clear to me that this is suggesting it has a whole lot more to do with the temperature coefficient of the wire, and I think especially that negative coefficient of the termination resistor, that ceramic unit. I don't know, perhaps I could look into maybe a you know, a metal foil resistor. I did look at some of those and they have a positive temperature coefficient, which might eliminate this this effect. Though truly, I don't think it's, you know, as I said before, going to make a big difference in performance overly. What an interesting phenomena, though. I think, you know, I think we can conclude, you know, obviously it's got nothing to do with frost or the frozen ground, because I can tell you for sure the ground is still just as frozen as it was a week ago. By the way, here, let me just do it here. I'm going to load the file. I'm going to load the graph of the east wire. So this is what it was like in the summer. I'm going to do a rescan. And look at that. Okay, it's not exactly the same, but, you know, very, very close compared to where it was when it was real cold. I suspect when it warms up even more back to summertime temperatures, that'll be a perfect match. Interesting stuff. 73, this is Steve, B6WZ.